Oh, I guess we should perhaps wait a couple of minutes for more people to join. Okay, I guess it's a good time to start. Are you ready?
Yeah.
Okay. Okay, so, welcome everyone. We're happy to have Chris Shriver of UCLA to talk about equilibrium of nearest neighbor interactions. And this is Chris's first talk, which is an introductory talk. And second talk will be next week on new results.
Thanks. Okay, so for the first, excuse me, bit of my talk, I'm going to be talking about the Ising model, which is a model for magnetism. So this was first introduced by Lentz, actually not Ising, but he gave it to a student whose name was Ising, who studied in his PhD thesis, and that was in the 1920s. So at this point, it's pretty well studied. So that, which is still going, I guess, is an animation that will eventually be explained. So first, I'll just say a little bit about what we imagine the magnet to consist of. So we have some particles which are arranged in a crystal lattice, and for simplicity, classically we'll assume that the lattice is actually a rectangular subset of the integer lattice C to the R. So each particle, the relevant data, as far as we're concerned for this model at least, is just a spin, which can be either +1 or -1. So you think of that as a little magnetic moment just for that individual particle. So the microstate of the system, which is what it's called, so this is describing the state exactly at a microscopic level, is then given by an element of + or -1 to the R. Right, so to set expectations a little bit, this is not really supposed to be taken completely seriously as a model of a real physical system. And what I mean by that is that we're not going to be making any kind of numerical predictions that we expect to really quantitatively agree with real life. What we do want is to see some kind of qualitatively accurate behavior. So specifically, we expect the magnetic moments of the individual particles to align with each other, at least under certain conditions, and produce a net magnetic moment in one direction or the other. So it's not supposed to be physical, but I can say a few things here in the next few slides about things that are maybe more realistic than you might expect. So I didn't know until fairly recently that real magnets actually do tend to have a crystalline structure. So you can see on the right there, these are some magnetite crystals. I think this is an especially nice example. Maybe they don't always look like this, but the black fridge magnets actually have a crystalline structure. The rare earth neodymium magnets actually have a crystalline structure. So our assumption that the particles are actually nicely laid out is fairly realistic and possibly important. Okay, and there's some rectangular looking ones if that makes you feel even better. Okay, so those are the components of our system. Some extra parameters. We are going to assume that there's some kind of ambient magnetic field given by a real number h, so that could be 0 if you don't want there to be no magnetic field. And there's some parameter, another real number j, which is going to quantify the interaction between pairs of particles. So if that's positive, then the particles want to align with each other. We call it ferromagnetic. If it's negative, then they want to go in opposite directions to each other. And that's called antiferromagnetic. But I mean, same in opposite directions. I'm referring to these spins plus or minus 1, by the way. So another assumption we're going to make is that the particles only interact with their nearest neighbors in sort of the cardinal directions, so not diagonally. And another physical comment, according to some sources, at least, the interactions that make the spins align with each other are not, it's not purely the electromagnetic force that makes that happen. And I think apparently just if you only consider the electromagnetic force, then you won't see this kind of spontaneous alignment. So it's actually a quantum mechanical interaction, which apparently helps justify considering only nearest neighbors. And also some of these fancy physics details make the antiferromagnetic interactions actually possible. Okay, that might be the last thing I have to say about physical realism. But okay, so we defined the energy of a microstate X using this formula. So the first contribution is energy due to interaction with the ambient magnetic field. So you can see that there's a lower energy if the particles tend to align with that field. Lower energy is good. And the second term, there is a lower energy if J is positive and the particles tend to align with their neighbors. So that V twiddle W, that's supposed to be summing over all pairs of adjacent sites in the lattice. Okay. So I talked about sort of how the system interacts with itself and with an external magnetic field. That's sort of the classical mechanics type of situation. So here's where the statistical mechanics comes in. So start talking about equilibrium. What I really mean is that it's not just an equilibrium with itself in isolation. We're going to assume it's immersed in a heat bath, because it's one more physical thing. So we don't need to go into exactly too many details about this, I guess, but the idea of a heat bath is that it has a constant temperature T, and it's so big that even as it exchanges energy via heat between the heat bath and the system that we're looking at, the temperature of the heat bath doesn't actually change. Okay, and then also very important that when we talk about equilibrium, we don't mean that the microstate is going to be constant over time. So if you think about, say, like a glass of water, when you're looking at it at the macroscopic level, it looks like it's in equilibrium, but if you were able to zoom in on it, you would see that the particles are still moving a whole lot. So the classical way to deal with this, the fact that even in equilibrium, we would expect the microstate to change, is to describe the system state by a probability distribution on microstates. And the way that's interpreted is that if you give this distribution a set of microstates, then it tells you how certain you are of observing the system to be in one of those states. Okay, and the effect of the temperature on this, now we can say, is that when you're in equilibrium at a higher temperature, there should be sort of more residual randomness in your equilibrium state. There should still be more motion at the microscopic level. So that justifies taking a little excursion here. Maybe this is familiar to everyone, but it's a quick slide on entropy. So if we're going to say more random, we need a way to quantify randomness. So in the context where we have a finite set and a probability measure on that finite set, the Shannon entropy of mu is given by this formula here, which, okay, we won't need to use, but that's what it is. Well, I need to use it. We won't need to use it in the talk. So this is supposed to measure how random the measure is. Or another way of saying what it is that it's the amount of information that we expect to gain by observing a random variable with law mu. Assuming we know what the law is, we just don't yet know what the value is. Okay, so here's some properties to build your intuition about it if you haven't seen it before. So no matter what mu is, the entropy is always non-negative. And it actually attains the value 0 at a point mass. So if you know with probability 1 exactly one state that the system is going to be in, then the 0 entropy is deterministic. And the maximum entropy is attained by the uniform distribution. So that's sort of like you have no idea, you have no information about the observable in a sense. And the value of that entropy is log size of the set. Second thing is if you have two independent random variables or product measure, then the randomness is additive. And the third thing is you have a mixture of two random variables, then the entropy of that is at least the average of the two entropies. So if you take a coin flip, if you make a coin flip and then if it lands heads, you draw from mu. If it lands tails, you draw from nu. That's kind of what is on the left-hand side there. And the right-hand side is saying it's at least the average randomness. And actually, unless mu is equal to nu, there's extra randomness, which you can interpret as coming from the randomness of the coin flip, which matters exactly when the distributions are different. Okay. Entropy. So now back into physics. So we can define the free energy of this probability measure, which is again supposed to be a statistical state of the system. And what it is the average energy minus the temperature of the heat bath times the entropy of the measure. So it is a standard principle in thermodynamics that I think is not completely justified mathematically, that whatever that would mean, that a system is in equilibrium when the free energy is minimized. So at least one heuristic for that is that, so as I said before, the system wants to minimize its energy, but then you also have the temperature of the heat bath, which is trying to increase the entropy a little bit, and you're trying to balance out these two influences. So that's why you might expect an expression like this, at least, to be minimized in equilibrium. So another interesting thing to point out here that will sort of be relevant later, we haven't mentioned any dynamics yet, right? So maybe you could think of this almost as like a free body diagram from high school physics, I guess, that you sort of know what forces are acting on it. You can say what the situation would have to be in order for nothing to change without necessarily having to like write down a differential equation and solve for the change being 0 or something like that. Okay, and at least in the finite setting, you can exactly calculate what the equilibrium measure is. So which measure actually minimizes the free energy. This is called the Gibbs measure, and it's proportional to this quantity, the exponential of minus beta times the energy. And beta is called the inverse temperature, and in a lot of contexts, it turns out to be a more natural quantity than the temperature itself. So that will continue to appear. Okay, so there is one Gibbs measure, and it satisfies this classical thermodynamics condition of minimizing the free energy. So that's what we think of as being the equilibrium state. Okay, but this is a problem because I said earlier that we're trying to model this property of a magnet where it can be either in one direction or the other direction. The spins can have two different states, two different equilibrium states. So that property of having an equilibrium, multiple equilibrium states, the system has that property. We say it exhibits a phase transition. And yeah, at least for some parameters, we should expect a phase transition. So this is not too surprising if we're at high temperature, because we know that if you get a magnet too hot, it will actually just lose its magnetization. But we should expect something a little different than this at low temperature for sure. And the standard solution is to instead look at infinite systems. So we're kind of blaming the problem on the system being too small. Okay. Okay. That's, I think, I find that a little unsatisfying to just say that, but we'll sort of get back to that, building a correspondence between an ideal infinite system and a finite system. We'll definitely get back to that more explicitly next week. But for now, we can look at infinite systems, which are supposed to be ideal in some sense. and see if they have the behavior that we want. Okay, so the approach that we're going to take to begin with, so we have these two notions of equilibrium. The first was the more fundamental one thermodynamically, was the minimization of the free energy. But then we also showed that the Gibbs measure is the equilibrium measure. So the first thing we're going to generalize to infinite systems is the notion of a Gibbs measure. Okay, but we immediately have a problem because the Gibbs measure was supposed to be proportional to e to the minus beta times energy. But energy was a sum over all these pairwise interactions and interactions with the field. So that's just not going to converge, right? Well, I guess in very specific cases it could converge, but there's no reason to expect it to. So this is not a good, we can't just generalize the definition using the same formula. What we're going to do instead is, you could think of saying a system as an equilibrium if every individual particle is in equilibrium with its surroundings. And we will use these finitary Gibbs measures to figure out what that condition looks like. So specifically, we're going to start by writing down the conditional probability of the spin at V being +1, given that the spins everywhere else are given by some labeling Y. Right. So if you just write that out, definition of conditional probability, that's what we have on the right-hand side. So we can plug in our definition of mu, the finitary Gibbs measure. Oh, by the way, this notation, I haven't used this yet. So this labeling Y with a superscript V2 +1, that's just you take the labeling Y and you relabel V with +1. Right. Okay, so plug in the definition of mu. Now all these terms with a big U, like I said, those are big sums, right? But what's nice about this setup is that we can cancel everything that doesn't involve V, and we end up with something that's complicated, I guess, but it only depends on the labelings that Y gives to vertices that are adjacent to V. So I will get rid of this ugliness and replace it with, upshot. Again, the conditional distribution, or the conditional probability of seeing a +1 at V, given seeing Y everywhere else, is just this function, which depends only on vertices, the values of Y at vertices adjacent to V. Right, and that we can extend to infinite setting. And the specific way we can do that to define this T sub V, so T is for tail, this isn't D sigma algebra, but so let T sub V be, it's not detailed sigma algebra, but let this be the sigma algebra, which contains all the information of all the information of the labelings at everywhere but V, which is what that's supposed to mean. And then we can say that a measure of mu is Gibbs if this C function, say as a function of Y, is a version of that conditional expectation. Actually, this should be, so that equation should hold, and then also the equation with a minus should hold. A minus both places that the plus is. Okay, and this should hold also for every V. Sorry, missing a few quantifiers there. Okay, so this is a very standard way of defining infinite volume Gibbs measures, at least in this particular setting. There's a much more general thing where you have to deal with marginals on finite sets instead of individual vertices. But in our setting, this is perfectly fine. Okay, so this sort of solves our problem to some extent. So in one dimension, Gibbs measure is actually still unique. This was shown by Ising in his thesis in a different framework. I don't think he had conditional expectation given a sigma algebra, but he showed the 1920s analog of this result at least. He incorrectly guessed that it was still going to be unique in higher dimensions, but it turns out that luckily, I guess, he wasn't right. In higher dimensions, there do exist multiple Gibbs measures, at least below a critical temperature. So that's pretty cool because that's what we wanted, right? So it's supposed to be some Curie temperature, above which there's a unique equilibrium state. And below that, we have a phase transition with a plus state and a minus state. Possibly, actually, in some cases, there's many more. Okay, so a few things that make this not quite a success. So mostly, maybe the biggest one is that the Gibbs measure idea, at least from the point of thermodynamics, was not supposed to be the fundamental object. So maybe we would want to have still some notion of free energy. And then again, the real physical systems are finite. And I know I said that we are not really trying to describe real physical systems, but it is sort of unsatisfactory that we have to resort to infinite systems and not say anything directly about the finite ones, but probably less big of a deal.
Maybe I could say a few things. So
sure.
There are these scaling exponents, which one can define using the Ising model, and they do correspond to real world phenomena. So these are, so there's a kind of universality principle that describes the behavior near the phase transition. I mean, it's something kind of like the central limit theorem, you know, in the sense that, well, the central limit theorem, you know, you expect that a lot of random variables are going to have normal distributions, even though they're not exactly given by or approximately normal distributions, even though the way that they are constructed or the forces that that lead to them are not exactly the same thing as the mathematical model. Anyway, in any case, there are these they're called scaling parameters that show up. Okay, I mean, it's a, and the other thing is that, you know, what you're looking for is that in the infinite system, we have two different, well, we can have multiple equilibrium states, and that corresponds to a non-analyticity in the free energy function. And so what you expect in a finite system is that the free energy will have a sharp change in with respect to temperature. So it'll have a sharp derivative, perhaps. It'll still be smooth, but it'll have a sharp derivative, which in the limit becomes non-analytic. Mm. So it's kind of like, well, we're looking at the infinite system in order to detect where the phase transition is and to get some intuition. Sure. Although, yeah, I get real world systems are finite.
Yeah. I guess, yeah, for that you actually need to know that as long as you're passing off the problem to another level, that you need to know that the free energy functions for the finite systems approach the free energy function for the infinite system, right?
Right, yeah.
Okay, cool, thanks. So, okay, yeah, so back to free energy, which you just brought up. So a natural thing to do if the free energy is going to be infinite is to try to define some free energy per site or free energy density, since it's the infinite size of the system, which is causing the infinite quantity. So a way to do this on our lattice, so we can look at the marginal of our measure of our state on a large rectangle. So this is 2n plus 1 on each side. We can look at the free energy of that marginal. We can divide by the volume and then send n to infinity. So here we're just taking a limb suit, so we don't have to worry about the existence of the limit. In nice settings, this will be, the limit will exist. So like if mu is translation invariant, like this limit will exist. So this is a fairly natural extension, so we can still define an equilibrium state to be one which minimizes A, the free energy density. But okay, for one thing, I guess it's not super clear that there's minimizing measures that actually achieve the minimum. But a bigger question that we're going to deal with is, are these the same as Gibbs states? So if I have an equilibrium state, is it necessarily this generalized Gibbs state that we defined a few slides ago? Okay, and the way we're going to actually study the relationship between generalized infinite volume Gibbs states and free energy density is using a notion of dynamics, which we'll introduce now. So I'll just give an intuitive description of the Glauber dynamics. So first I'll say how we can evolve a microstate. So we assign to each site in our infinite lattice. Actually, we can do the same thing on a finite lattice, and we'll need to in a second. We give each site a Poisson clock, which is some imaginary clock which rings at independently distributed time intervals that are all exponential distribution with rate 1. So whenever one of these clock rings, you re-randomize the spin at that site using the probability distribution given by this function C. So the dot is just to indicate that it's a function of plus or minus 1. Okay, and so that was exactly the conditional expectation that the Gibbs measure is supposed to have, right? Conditioned on y. And y, so y is supposed to be the state of the system immediately before re-randomizing, so immediately before the clock rings. Okay, so that's how you evolve a microstate. And here is a video, which is fun to watch a little bit of. I'll maybe skip ahead a few times. So we're starting in a random state at a relatively high temperature, I guess. So everything is sort of randomly evolving. Well, it's definitely random, but relatively more random. So let's skip ahead a little bit. So now the temperature is lower, and it seems like these sort of shapes are forming, but the boundaries of the shapes are still fluctuating quite a bit. This is at the critical temperature. Let's skip ahead a little more. The shapes are bigger, and as the temperature goes down, the boundaries of the states, the boundaries of the shapes sort of seem to be stabilizing. Yeah, this video stops before this happens, but eventually, now that we're below the critical temperature, we should expect this to be mostly one color eventually. Okay, so that's what was on that first slide. Okay, so that's how we develop a microstate. But the state of our system is supposed to be a probability distribution. So we just quickly say how we're going to evolve one of those. I guess that's what you'd expect. So you first draw a microstate by the distribution. You evolve that microstate, like we said, for however much time you want. And then your evolved distribution is defined to be the law of that evolved microstate. Okay, and something which is not too hard to see is that Gibbs measures are going to be Glauber invariant. This is almost by definition because we define the Glauber dynamics by re-randomizing these sites according to that Gibbs conditional marginal thing. Okay, so it's not the converse of that is a lot less clear though. So if I have a Glauber invariant measure isn't necessarily Gibbs. I guess it might seem clear at first, but it's not. So Gibbs are supposed to be invariant under re-randomizing individual sites, but once I throw in this randomness of which site I'm choosing to re-randomize at different times, that just complicates things a little bit. Okay, so yeah, so first we'll talk about the connection of Glauber dynamics to free energy. And this is in back to the finite case, just for a slide. So there's a useful quantity in information theory called relative entropy. So again, in the finite case, if you have two distributions P and Q, it's defined by this entropy-looking formula. And a neat fact is that if I have a sequence of measures on X, which are evolving according to some Markov transition kernel, and then I have some other measure mu, which is stationary, so invariant under the kernel, then the relative entropy is non-increasing. So I guess you can, there's a book on information theory by Glauber and Thomas that has a lot of this stuff. So if I apply this fact in the setting where, so say I start with some zeta, which is any state on the finite system, and then let mu be my Gibbs measure. And I don't think I've used this before, but Z I'm just using to be it's called the partition function. It's how we normalize, that is what we need to divide by to make this a probability measure. You can do this calculation and you get not exactly the free entropy, but sorry, not exactly the free energy, but free energy times a positive number plus a constant. So the free energy is actually non-increasing also as zeta evolves over time. And maybe one aside comment. So I've talked about like free energy density, specific free energy of, so some authors will use this to mean something different. Actually, a lot of authors will. So sometimes they'll mean this to be the limiting free energy density of the Gibbs measure, but I'm talking about something slightly different. Okay, so if you don't know what that is, then just don't worry about it. But, okay, and I guess some authors will also call this the relative entropy density. Or we'll use the relative entropy density instead of the free energy density. Maybe it's more accurate. Okay, so that was a finite case. You can't just do exactly the same thing in the infinite setting. Things don't work out, fortunately. But the analogous statement about free energy density and infinite dimensional Glauber dynamics is true. So if you start with any state and evolve it under Glauber dynamics, then the free energy density does not increase. Okay, so to take this a little further, we need to introduce shift invariance, which is what we expected to be. I mentioned it earlier. If you take any set of labelings E and you shift all those labelings by some fixed amount to get a new set, those two sets have to have the same measure for it to be considered shift invariant. So physically, this means that the system is homogeneous, I guess, in a sense. Because if someone wants to jump in, I don't have a super great sense of why you would need to require something like this to get the following results. But if you're coming from ergodic theory, it's a pretty natural thing to require, right? They were looking at a measure preserving system. It's just a measure with a measure that's preserved by the natural action of the lattice on itself. Okay. But in any case, if you do make this assumption, then free energy, you can say more than just free energy being non-increasing. You can say that if you start with a measure that's not Gibbs and evolve by a strictly positive amount of time, then energy actually has to strictly decrease, the free energy, I mean. So what this means is that if you start with a shift invariant equilibrium measure, then it has to be Gibbs, because equilibrium means you're already at the minimum of the density, right? So it can't decrease anymore. Also, if you start with a Glauber invariant measure, then it's not going to change. The measure is not going to change at all. So definitely the free energy and density is not going to change. So it has to be Gibbs to begin with. So that nicely connects several of these notions of invariance. Because, I mean, I haven't mentioned this explicitly, but when we introduced dynamics, we introduced the whole a third notion of equilibrium, right? Which is that you're invariant under Glauber dynamics. So it's good to see that that's also the same.
I imagine that this function A might not be well defined if the measure is not shift invariant. A is defined by a limit, and maybe that limit doesn't exist necessarily.
Or it depends on the Fulner sequence that you use, right? I mean, I did say a lim sub to begin with, just to be safe.
Oh, I see.
Yeah. But yeah, he does definitely use in the proof here that there is actually a limit. So yeah, I mean, you can look in the proof and you can see like, oh, this definitely would not work exactly what he did if it was not shift invariant. But yeah, I don't know. I don't have a physical reason why this should not be true if it's not shift invariant, is all I mean. Right, so something to say but not get into. So I've said that every equilibrium measure is Gibbs. We also wanted every Gibbs measure to be an equilibrium measure. That's true in this setting, but I'm not going to get into that, I guess. And it's not going to be exactly true in the bigger setting that we're looking at next week. There's going to be some caveats to that direction. Okay, so I want to say something about the proof of specifically the first thing. So this free energy density, so it's a limit, original lim suit, but like we've said, under this context, it's actually a limit. So it's a limit of these free energies of the marginals. And so not using the definition of Glauber dynamics I gave, but using a different definition, you can pretty easily write down at least an expression for the time derivative of the free energy of a marginal. And it'll be a little complicated, but I guess if you're Holly, then you can rearrange things in a way. So you can see that this derivative is actually non-positive is our direction, right? So it's non-positive, but there's a little bit of an error term, which does go to 0 as n goes to infinity. And one way of seeing where the error term is coming from is that, so I'm looking at the marginal of the system restricted to a large rectangle, then that's not actually going to be a Markov chain. It's going to have some interaction with the rest of the system. So remember the last slide, we were looking at the non-increasingness of relative entropy on finite Markov chains. So you're kind of using that, but you don't actually have a Markov chain. You have something which is on short enough timescales, at least approximately a Markov chain. The reason that works is because when you're only interacting with the outside, you're looking at, so you're only interacting with the outside through the boundary of a larger rectangle. The boundary is small compared to the volume of the rectangle, right? So in some sense, then there's not really too much interaction with the outside. So the Markov chain, you can approximate it by a Markov chain, and that approximation only gets better as the volume of the rectangle goes to infinity. Okay. So we will come back to that description at the very end. So there's one more thing which I'm going to generalize that I like, good to mention. So I've shown that we've shown this equivalence between these different equilibrium states. So now that we have dynamics, though, it's natural to ask whether we actually approach equilibrium as t goes to infinity if you start with something that's not in equilibrium. So again, in the shift invariant case, that is true in this specific sense, at least. So what I mean by approaching the set of Gibbs states is if I take an open neighborhood of the set of Gibbs states, then for all large enough t, we're eventually in that set. Of course, large enough depends on where we start, right? But yeah. Or in other words, if you look at a mu t as a function of t, every limit point of that is a Gibbs measure. So this is sort of a white lie version of what the proof says. So we have this function a of mu t. So you can think of this as a function of the measure of mu t, but it's also a function of the time parameter t, right? So the time derivative is strictly negative if you start at a non-Gibbs measure. And as a function of the measure, it's upper semi-continuous. So a more accurate version of what it actually says is that if you have a non-Gibbs measure mu, there's some neighborhood of that measure mu. So every time the dynamics enters that neighborhood, the free energy decreases by a fixed amount. So since free energy density, I keep saying free energy, I mean free energy density, sorry. It's bounded above and below uniformly. So you can't do this an infinite number of times, or else you go down to minus infinity. So that means that every limit point has to be a Gibbs measure. Okay, so that's the end of the first section on Ising model related things. I have a few more slides on what I call the motivating non-amenable example. Okay, so last few slides are going to be on independent sets and independent set problem. So this picture on the right is a graph, and the blue vertices form an independent set. What that means is that no two blue vertices are adjacent to each other. And it looks like a sparse set, but in this case, it's actually maximal in that you cannot add another, well, you can't color any more vertices blue without having two adjacent blue vertices. Okay, so the first two bullet points are just saying that. Definition of independent set. So this is a basic example of a constraint satisfaction problem. The constraint is just having no two adjacent vertices. A nice thing about this particular constraint satisfaction problem, CSP, I guess, if you want to sound cool, is that there's always a solution, which is the empty set. So that's not true, for example, if you're trying to two-color a graph, or I shouldn't say that. So coloring algorithms, yeah, might not have a solution. It's not obvious that they have a solution. Coloring problems. I'm looking at the word algorithm right now, so I said it. Also, there is a natural greedy algorithm if you want to produce something larger than the empty set, which is to keep randomly choosing vertices and include them if you can do so without breaking the constraint, and stop when you can't choose anymore. Okay. So you can definitely find some independent sets. It's more difficult to find large independent sets. And yeah, just fun fact that this problem is NP complete. And I think it's actually a typical example given when you're defining the class of NP complete problems. Okay, so here's a slightly different algorithm just to round things out a little bit. What we can do is we can take our graph, define a graph, and put labels on all the vertices that are real numbers between 0 and 1, and identically distributed and independent. And if we let I be the vertices whose label is strictly larger than any of its neighbors' labels, then that's going to be an independent set. Independent because of a strictly larger condition. It's always independent. So if G is a deregular graph, then for every vertex between it and its D neighbors, that's D plus 1 vertices, all of them is equally likely to have the largest label. So the probability that the central vertex is the one that's chosen or is chosen is 1 over D plus 1. So linearity of expectation tells you that the expected size of the independent set is size of the vertex set over D plus 1. Okay, so this is nice because this is an algorithm that can be run in constant time as long as you allow parallel computing, because you're only looking at, I guess if you imagine there's a computer situated at every vertex, and each computer comes up with its own random numbers and then talks to its neighbors, and figures out who has the biggest one, and then sends up a 1 if it's the biggest of itself and all its neighbors. So in that sense, it runs in constant time because each computer takes a finite amount of time to run, independent of the size of the vertex set. But as you can see from this last bullet point, it actually doesn't do very well, because you can show that a typical d-regular graph has an independent set that's density 2 log d over d. Right. So actually, there's more sophisticated constant time algorithms. They're also called, more specifically, they're called local algorithms that get close to half of this maximum value. But also the greedy algorithm gets about half the maximum density. Okay. And I think it's true that there are no known efficient algorithms that get strictly better than half the maximum density. But someone can yell at me if that's not true. Okay, and it's actually known that so-called local algorithms cannot do much better than half the density, half the maximal density. Okay, so back to something related to what we were talking about before, something called a hardcore model. The term hardcore comes from physics. This was proposed at some point as a model of a gas, but I think physicists sort of can't decide whether, well, okay. At some point, physicists stop caring about it anymore. And then I think some of them do again. So to get closer to the setting we were in before, instead of looking at subsets of V, we can look at labelings of the vertex set by zeros and ones. So 1 is in the subset, 0 is not in the subset. And we can define a measure of mu on labelings of V, defined like this. So here, this absolute value of x looking thing is the cardinality of the associated subset of that labeling. Z is a normalizing constant, and lambda is a positive number called activity parameter, or fugacity, I've also seen it called, if you like Latin. So bigger lambda means that this distribution is placing more weight on large finite sets, right? And actually, if you have a small positive lambda, it's placing more weight on small independent sets. So we definitely, if we're looking for large finite set, large independent sets, since those are the hard ones to find, then we want to look at large lambda. Okay, and this is something I don't know much about, but could be fun to mention. So sampling from this, being able to sample from this distribution has been shown to have some relevance to computational complexity problems. So there was a recent paper about RP equals NP, which unfortunately had to be retracted, that was related to sampling from this distribution. Okay, so we can write it in a form which, aside from this indicator function, is a Gibbs measure, right? So we can define a temperature to be minus log lambda. We can define an energy, which is the size of the set. And then mu from the last slide can be just written in this form. So it's a nearest neighbor potential with a hard constraint, but the hard constraint itself is actually a nearest neighbor constraint. So that's not too bad. The potential itself is actually not even, doesn't have anything to do with the neighbors, it's just individual spins. So given the similarity to the Ising model setting, we can define an analogous Glauber dynamics, which should have this distribution as its stationary distribution, and moreover, it should converge to this distribution as time goes to infinity. So we can actually use this to at least approximately sample from mu. So unfortunately, this tends to converge pretty slowly to its stationary distribution. So at least in the worst case scenario, it converges slowly if you start at a bad starting point. Okay, but in any case, I think this sort of motivates considering this dynamics in this slightly different setting. So one thing about it is, so we could sort of justify the Ising model just looking at the integer lattice, but now that's not really a natural setting anymore. We want to look at more general graphs to look at constraint satisfaction problems. So one common setting is a random regular graph. So these are hard enough to be interesting, but still have some regularity to them. So one fact about a typical large random R regular graph is that it locally looks like the infinite R regular tree near most vertices. And we'll be more precise about that next week. But basically there are not too many small loops in a large R regular graph. So it's locally tree-like. So this suggests that the ideal infinite graph in this setting should be the R regular tree. Oh, I just saw this thing in the chat. Okay, yeah, thanks. So an unfortunate fact that we'll have to deal with is that now in this ideal infinite graph, as a non-ideal property, that large subsets of it do not locally look like itself. So as you can see in this picture on the right, a significant fraction of the vertices are actually near the boundary, and this fraction does not vanish as the size goes to 0 either. So this is basically the same fact as saying that a free group is not amenable. As a free group scaly graph is a infinite tree. So the consequence of this is if we tried to run through that whole program we had for the Ising model, the error coming from outside influence, when we would say running the marginal on a, so running the dynamics on a finite marginal, that error will not go away. Because so if we look at a large subsystem of the infinite dynamics, you can't disregard the influence from the rest of the system. Okay, and it's sort of questionable whether you'd want to do that anyway. So maybe this is, yeah. So we wanted to look at large regular graphs anyway, not large subtrees of the infinite tree. Okay, so this is a lot of stuff going on. This is the last slide. So let me get my laser pointer. Okay, so this is a picture of what I've been talking about a few times. So we have this framework where we have a state on the infinite lattice, and then we can pass to a state on a large finite subset. So we can pass to our finite subsystem by just taking a marginal, right? And what I was saying was basically what made Hawley's proof work, was that this diagram approximately commutes. That if you first take a marginal and then run Glauber dynamics just on that subset, where you're just totally ignoring outside influence. So on the other hand, you can first run infinite Glauber dynamics starting at the same state and then pass to the marginal, and that will be taken into account outside influence. Those are approximately the same thing, which is what this little approximate thing is. And the approximation gets arbitrarily good the larger the rectangle R gets. Okay, but now what I propose doing is let these large typical random regular graphs replace the large subsystems, because those, we know that a large typical random regular graph does locally look like the infinite tree. So here, I'm writing FR instead of TR, just because I'm thinking about it as a group now. And then I want to come up with some similar setup where I can do this, but now I have something which is not actually a subsystem of the ideal infinite system. So I can't just pass to a marginal. So it's not really clear what this operation should be. But there is something which fits in here. Yeah, and that's the part of it which is going to come from Lewis Bowen's sofic entropy work. Yeah, and I'll be able to use that to prove generalizations of, I think, all of the theorems that I mentioned to a lot of non-amenable groups, but not all groups, and also not all sofic groups, unfortunately. Let's see. Yeah, okay, and I guess a final comment. Even if you're just looking at lattice systems, I kind of like this extrinsic approach anyway, because an ideal crystal is not going to be, a real crystal is not going to be an actual sublattice of the infinite lattice. It itself is just going to locally look like the infinite lattice. So it does seem like a more natural condition to me, even if you don't want to go beyond integer lattices groups. Okay, that's all I have for this week.
Okay. So thanks. Yeah. Well, I'll open it up for questions.
I'd like to make a bit of a comment on sort of the whole general setup.
Okay.
Sort of let me switch to my own document camera. And it might be
I can
better
make you the co-host.
Actually, I don't need that. Just you might want to stop sharing so that way I'll pop up bigger.
Right. There you go.
So that sort of the problem from a physics perspective, the problem of statistical mechanics is you typically have some subsystem. And it's sitting inside of a big system. And ultimately, this whole thing is sealed. Right? The subsystem might be your lab, and then the whole system is the entire Earth. That is, okay, it gets, apart from getting energy from the sun, it's a closed system. And what you've got is a certain total amount of energy. And you're trying to figure out what are all the possible states that you could have in here. And the only game in town is entropy. But the entropy has different pieces. It's got the entropy of the subsystem. That's got the entropy of the stuff that's outside. And you're going to take a limit as the size of the bath. You basically treat this as a heat bath. This is something, the total amount of energy is fixed, but you can put more of it in here and less of it in here, or you can put more of it in here and less of it in here. The more energy goes outside, the more the entropy of the outside goes up. And you can make an approximation that S out is a constant plus another constant times the energy. You just make a linear the energy that's out. You call this constant beta. And so effectively, if you're trying to maximize the total energy, that's the same thing as maximizing the total entropy. That's the same thing as maximizing the internal entropy plus beta times the external energy. That's the same thing as maximizing the internal entropy minus beta times the internal energy. Okay, you usually divide here, you multiply by -1, and you call this the free energy. Here you got your energy inside, and this is the 1 over beta is your temperature. So this whole idea of talking about free energy comes from the fact that you're sitting in this, there is an outside. There's this big outside, which is big enough that the entropy of the outside is a linear function of its energy along the scale of all the energy fluctuations that could possibly happen inside. So you take the limit as the outside gets infinitely large, and you assume that it's a perfect heat bath. And now you've got a description of the inside. And the inside is and you say, oh, well, that is given by the Gibbs distribution. You've cheated a little bit because you've ignored what happens, all the interactions right on the boundary. Now you're going to take, but now you take a limit as the internal guy gets bigger and bigger and bigger and bigger. And as long as you're not sitting, in most cases, as the internal guy gets bigger and bigger and bigger, what's happening in the middle is all that really matters. The boundaries don't really matter. Everything's amenable, so there's much more volume than there is surface area. And there's a well-defined limit as you take things bigger and bigger and bigger, and you've got this unique Gibbs state. But if it's too cold, then you discover that, you know what? When you have more than one Gibbs state, what that really means is that what happens in the middle is sensitive to what's happening on the boundary. That the way you put your boundary conditions on the subsystem wind up mattering. And so you have lots and lots of different states. So you could wind up with several different Gibbs states, and they basically correspond to different kinds of boundary conditions that you can put on this big system as you take the limit as this big system gets bigger and bigger and bigger and bigger. And now we're going to try to do this in a non-amenable setting. And in a non-amenable setting, even when you've got a single Gibbs state, the boundary doesn't go away. If you're in a hyperbolic setting, the boundary is a finite fraction of the whole thing. That makes things hard. That makes things really interesting. And so if you can make some progress on this and come up with a all of these machineries about infinite volume Gibbs states and equilibriums for Glauber dynamics and this, that, and the other thing, are various ways of abstracting the limits as you first take this region to infinity and then take this region to infinity. And if you can make sense of that in the non-amenable case, that would be really, really cool.
Well, I made sense of some things to myself, but I'm not at the level of understanding of the thermodynamics perspective as I'd like to be. So hopefully I can show you some things next week and you can tell me.
Yeah, no, that sounds great.
But yeah, thanks for explaining that.
Okay, so.
And I can never pass up a chance to use my document camera because I love that tool.
Okay, well, so I guess we should thank Chris. The only way we know how. And I guess that's it for today. If there are no more questions, I mean, if there are, then please ask. So thanks, Chris, for the nice talk. And I guess we'll see you on next week.
Thank you.
Yeah, okay, great.
Thank you.
Thanks again.